So let me start. So this is the history lecture for my advanced nuclear physics course. So, okay, so far I have explained the microscopic mean field approaches to describe nuclear many-body problems. And today I will explain or introduce these time-dependent extensions of Hartree-Fock density function theory. And I will show some applications to describe nuclear reactions and dynamics. Okay, and again, this is just a syllabus. And okay, so far I have explained what is Hartree-Fock and DFT, density function theory. And I have introduced this, how to describe pairing correlations. So we learned a bit about BCS and HFB theories. And last time I explained some methods to describe collective excitations. So in this lecture, I introduced the TDA, time-Danforth approximation, and RPA, random phase approximations. And we have learned that collective excitations can emerge as a superposition of particle-fold excitations. And yeah, today I will explain time-dependent Hartree-Fock and DFT. And first, in the first part, I will derive RPA from the linear response, small amplitude limit of TDHF theory. And then I will apply it to describe more, non-linear, complex dynamics like low energy heavy ion reactions. And in the rest of two lectures, I will discuss applications for the physics of neutron stars. Okay. So this is the purpose of today's lecture. So first, I will explain what is TDHF, time-dependent Hartree-Fock, and again, I will discuss its relevance. So what is similarity and difference between TDHF and TDDFT, time-dependent density function theory. Okay, and then I will explain about the linear response theory, and I will derive RPA from TDHF. And then I will apply TDDFT or TDHF to describe nuclear reactions or heavy ion collisions at low energies and demonstrate its usefulness. Okay, so the main purpose is to understand how we can describe complex nuclear dynamics based on microscopic theory from nucleonic degrees of freedom. Okay, then first I will explain the time-dependent Hartree-Fock theory. Okay, so those are Hartree and Fock, and here I put the picture of Dirac. And actually, the TDHF theory was first proposed by Dirac, in 1930, already. And nowadays, we use this approach and some extensions to describe nuclear reaction dynamics. Okay, so this is just a recall. So about the Hartree-Fock theory that we learned in lecture 2. Okay, so I will go quickly. So this, so the Schrödinger equation could be derived based on the variation principle. So without any restriction to the many-body wave function, we could derive the Schrödinger equation. And what was Hartree-Fock approximation? So in the Hartree-Fock theory, we approximate this many-body wave function psi as a single theta determinant. So that was the point. And using this theta determinants, so those are just the expressions of theta determinants, and phi, small phi, denotes the single particle wave functions. Okay. And what we did, so we derived based on this variation principle using theta determinant, the Hartree-Fock equations. Okay, so now we extend this variation principle to the time-dependent regime. So now we derive the time-dependent Hartree-Fock theory. So first of all, the time-dependent Schrödinger equation, so-called TDSE, can be derived from an unrestricted variation of this kind of action. Okay. So in the static case, we just take the energy expectation value, but in the time-dependent case, we take this kind of action with this time derivative. Okay. Then again, by taking the variation of the Bragg states, you can easily derive the time-dependent Schrödinger equation. So, okay, so this is just the explanation of some properties of TDSE. So we can easily show that the norm is conserved for all times, during the time evolution. So we can take this time derivative of this norm, then you can get this kind of equations. So you can replace this psi dot using this TDSE, time-dependent Schrödinger equation, and then you can find that this is 0. So norm is conserved. And also, we can show that energy is conserved. So similarly, we can take the time derivative of this total energy, and then in this case, you can use in the opposite way. So H psi can be replaced with this IH bar psi dot. Then you can find that the total energy is conserved. So this is the properties of TDSE, time-dependent Schrödinger equation. So now, again, so as you can expect, so in the TDHF theory, again, we approximate the many-body wave function to be a single theta determinant for all types. Okay, so that's the point. Okay, so in Hartree-Fock, static Hartree-Fock case, we have derived the expectation value of this Hamiltonian. So what is new is this time derivative part. And then let me explain briefly how to calculate. But it is very similar to the one-body part. So now we take this kind of expectation value, let's say, of this IH bar del T. And then, okay, so this is again the same. So we can show that all the n factorial terms which emerge from one of the theta determinants contribute equally. So we can, for all the terms, we can change the variables, those integration variables, and then the exchange of variables generates the minus sign from this the other theta determinant, and then all the terms contribute equally. And then here we have this IH bar del T. And please be careful that this time derivative operates for all the functions sitting on the right-hand side here. So this is just a trick. So since this time derivative acts every single particle wave function separately, so we can write down in this way. So it is similar to the one-body operator. So now we have a time derivative that operates on this i's coordinate, this side, this phi. Okay, and then we have this summation over I. So this is just the summation of all terms that operates this time derivative operator on each single particle wave function. So this is exactly same as one-body operator. Then we can use this orthonormal relations that generates Kronecker deltas, and what will be remaining is just one single term. Okay, so we have this equation. So this is just the same as one-body operator. So as you can see, if we take a time, variation with respect to phi star, it will generate, h bar, IH bar del T phi. So indeed, so with this approximation, we can get this time-dependent Hartree-Fock equation. So the right-hand side is the same as static case, and in the left-hand side, we have this new term coming from this time derivative part. But this is like TDSV, right? So the energy, in the stationary case, we have a single particle energy times wave function, but it is replaced with IH bar del T. Okay, so this is the TDHF equation. So in general, it can be non-local, but with effective interaction, local effective interaction, it will be local again, similar to the Hartree-Fock case. So this is just, I'd like to mention here that, okay, in the same way as TDSV, we can show that none or this overlap between single particle wave functions are conserved for all times. So we can take time derivative of this this overlap, then we can show that similarly it is 0. So this time derivative is 0. It means so in the initial state, we have single particle wave functions which are also normal to each other. And then we can evolve in time. Then automatically, based on the TDHF equation, this also normal condition preserves during the time evolution. So Pauli exclusion principle is automatically ensured for all times because of this property. So even for the case we have two nuclei and make a collision, then it is very complicated, but automatically, based on this equation, the Pauli principle is preserved. So it is a good property. And of course, we can show that the total energy is also conserved. So we can take a time derivative of total energy, and then in the similar way, we can show that this is conserved for all times. Okay. So this is very similar to time-dependent Schrödinger equation. And this is just the end of introduction of TDHF, time-dependent Hartree-Fock.
It's analogous.
Hmm?
It's essentially analogous to time.
Yeah, only this is a difference.
Yeah.
Okay. So now I will explain what is TD-DFT. So this is, as you can see, time-dependent DFT, so time-dependent extension. And in the density functional theory, so this is the reminder, okay, of lecture 2. So in DFT, the static case, what was behind in DFT is the Hohenberg-Kohn theorem. So based on Hohenberg-Kohn theorem, this theorem, so it shows that many-body wave function psi can be written as a functional of one-body density. So there is a one-to-one correspondence. Then any observable, like total energy, can be described as a functional of one-body density. And then we can take a variation with respect to this density. And in principle, we can get the true exact solution of many-body Schrödinger equation. Okay, so this was the static case. And in the TD-DFT, we have different theorem. It is not the Hohenberg-Kohn theorem. And we use somewhat different technique to show the existence of such a cell. So let me, okay, so this is the image. Okay, again, I will explain first what is TDDFT, just the concept of TDDFT. So in non-relativistic quantum mechanics, what we'd like to do is to solve this TDSE, time-dependent Schrödinger equation. Okay, for many body system. But it is, of course, in principle, impossible. I mean, in practice, impossible to solve. Okay. So here, I described the time-dependent quantum equation. So this is again similar to the TDHF equation. Okay. So the TDDFT shows that, okay, so there are two equations, completely different equations with different initial states. But according to the Hohenlohe theorem, at initial time, okay, let's assume it is a ground state. Then we can show that in principle, those two can be equivalent. Okay, in principle. So in the ground state, it is a constant equation, and this is a Schrödinger equation. And if we have exact universal energy density function, those two can be equivalent. And now we can evolve it in time. Okay, so it develops in time in a different way. It is not equal because the equation is different. But we can show that for all times, the many-body wave function, it is now time-dependent, can be written as a one-body density. It is time-dependent. And there exists such an energy density function, which provides the same one-body density, same time evolution of one-body density. Okay. So this is, okay, it is magical, but yeah, it is it explains what is TDDFT. So let me now introduce the basic theorem behind the TDDFT, which is the Runge-Gross theorem. Okay, so this theorem was published in 1984 in PRL. Okay, so this is just a notation and preparation. So this is just a definition of one-body density law. So it is, okay, psi is many-body wave function. So we can integrate out all the coordinates other than 1, and we can get the one-body density. And similarly, this is the one-body current density. So this is the definition. Okay, and then I will use those time-dependent Schrödinger equations. But the reason why we have two equations is because we assume different Hamiltonian. But the difference is only the external potential, this V external, V and V prime. So we denote it as H and H prime. Okay, so the kinetic part T and interaction part B are the same. Only the external potentials are different. Okay. Yeah.
Confused. So why is there a one body current density if we're talking about multi-particle systems? I'm sorry.
Oh, this is because I will show that exists a one-to-one correspondence between the many-body wave function and one-body densities.
I can just condense it into a single. Okay.
So let's see. So now I just take a time derivative of this one-body current density J. Okay, then you can take a time derivative of this psi star and also this psi, nabla psi, and this psi and this nabla psi star. Okay. And then you can use this TDSE to replace time derivative with, yeah, this h psi divided by IH bar, something like that. Okay, so we just take a time derivative of current densities and used TDSE to get this equation. And the difference between these two equations, yeah, this is the first one describes as J. The other one is J prime. So those are associated with different H and H prime. So namely, difference is this external potentials, V and V prime. Okay. Now, we can subtract the equation B from equation A. The left-hand side is nothing but this difference, time derivative of this J minus J prime. And the right-hand side, I skipped the details, but again, so this one-body kinetic term and the two-body interaction terms are the same. So if we take the difference, those two terms are canceling exactly. So what is remaining is this term associated with these external potentials. And we can get quite easily this equation. Okay. So yeah, this rho is the one-body density. And here, this is the nabla. So spatial derivative of the difference of the external potentials, V and V prime. Okay. Then, now you see. So if this difference between V and V prime, V and V prime, so these external potentials are different more than a time-dependent constant, then this right-hand side will be finite. So it means that if external potentials are different, then the time derivative difference of current densities, time derivative of difference of current densities is non-zero. Okay. So it shows that the one-to-one correspondence between the external potential and the current density. And one can also use the continuity equation. Okay. So continuity equation is this. So you can take the divergence of this equation, then it will provide you the left-hand side will be the density, time derivative of the density. And similar equation is for the right-hand side. So we can similarly show that if the external potentials are different, then the rho and rho prime must be different. So in this way, this Runge-Gross theorem shows that there is a one-to-one correspondence between the many-body wave function psi and the one-body density and the current density for all times. Yeah, because we can show that this correspondence at the initial state, and we can use some kind of Taylor expansion, and we can show that after small time step, this holds as well, and we can show that we have this correspondence for all times. So this is the basic concept of DFT, TDDFT, what Runge-Gross theorem tells us. Okay. So anyway, yeah, if you believe it, yeah, there exists yeah, we can have this, we can write down many body wave function as a function of one body density for all times. And similarly, based on the variation principle, we can derive the time-dependent function equations. Okay, so this is the first main topic of this lecture. And then we can actually apply this TDDFT to describe various phenomena in atomic nuclei. So I just picked up some representative examples. So first one is, okay, so this is the excitation, isobector giant dipole resonance. So this is the out of phase oscillations of neutron and proton densities. And this cross section shows the photoabsorption cross sections. So as I probably mentioned before, the interaction between heavy nuclei and some nucleus provides you some external kick only on the protons, and it excites this isobector GDR excitation modes. And those purple dots correspond to the experimental data, and those lines, especially this black line, corresponds to the result of TDDFT calculation. Okay, so this is as a function of excitation energy. So without adjustable parameter to describe this excitation modes, you can see that it agrees quite nicely with experimental data. And the other example is the fission dynamics. So we can prepare by solving the Kohn-Sham equation some elongated nucleus, and then we can evolve it in time. So we can dynamically see how heavy nucleus fissions. And after fission, we can calculate the average number of particles, kinetic energy of fragments, excitation energy of the fragments, and so on. And we can compare with experimental data. And also, we can, of course, apply this TDDFT to describe the low energy heavy ion reactions, which I will explain later. So we can prepare two nuclei, ground states of two nuclei, projectile and target, and we can make a collision by putting some momentum between these two nuclei. And then we can follow in time what happens during the time evolution. So microscopically, we can describe low energy heavy ion reactions. And what's more, so we can apply the same method to describe dynamics of neutron star matter. So this is peculiar example of application of TDDFT, including pairing correlations. So superfluidity is taken into account. And then we can describe the so-called quantum vortex. So this is some topological excitation of superfluid medium, and we can simulate the interaction between vortex and the nucleus.
Wait, so what is the
Vortex of superfluid neutrons. Yeah. So, and this will be the topic of my last lecture. Okay. I will introduce this. Okay. So anyhow, based on TDDFT, we can describe a variety of phenomena without empirical, parameters. We just use the same energy density function that describes all the properties of finite nuclei and nuclear matter, and then we can get those results just after some days of calculations. So it is very powerful.
But it's very computationally heavy.
Yes. So without pairing correlations, it is like with 100 CPUs, one day calculation.
Okay.
And with pairing correlations, it will be much heavier, 100 or 1,000 times heavier. So we need some techniques, special techniques, like GPU machine, like Tsubame.
Mhm.
Yeah. So this is high performance computer.
Not a laptop.
Not laptop. For small collisions, like, yeah, we can do it on the laptop, but yes. So anyway, it is very powerful too. So now, as a next topic, I will derive this RPA, random phase approximation, based on the TDHS theory. Okay, so this is one important point. I mean, yeah, I think you should know this kind of knowledge. So I put this in my lecture. So we can, yeah, derive RPA based on the linear response theory. So let's see. Okay, and this is, okay, so let me just explain what was the one-body density matrix in Hartree-Fock basis. So in Hartree-Fock state, we can define the one-body density matrix in this way. So this is just a definition. Okay, so log 0 is a one-body density matrix, and KL is a KL matrix element. And it is defined as this sandwich of AL dagger AK. And then, since in the Hartree-Fock state, yeah, the particles are, we have occupied state up to the Fermi energy, and after that, all the states are empty. So this one-body density matrix has very simple form, like this. So it has only one as a diagonal component for the whole states, and others are 0. Okay, so we call this part whole particle, particle whole, and particle components. And it has peculiar properties, the so-called idempotent property. So rho 0 square is rho. So square is itself, it becomes itself. Okay, and those are just a preparation, but so since it has this particular structure, this one-body density matrix can act like a projection operator. So if we apply this density matrix to some arbitrary matrix A, so since it has this form, it can pick up only this top components, okay? This whole and whole particle. And if you multiply this one-body density matrix from the right-hand side, you can take these two components, right? And then if you multiply from the both sides, you can take this whole part, okay? And we can define also this I minus rho 0. So I is just a identity matrix. And I just denote it as sigma. And then, since sigma has this form, it is 1 only for this particle part. So it can take these lower components. And if you multiply this sigma from the right, you can take this right-hand side, these right components. Then, if you multiply from the both sides, sigma, then you can get this particle component. And yeah, in the same way, if you multiply rho sigma, you can take whole particle component, and if you do it in opposite way, sigma rho, you can take particle whole component. Okay, so those are just preparation, and yeah, again, sigma square is equal to sigma, and since this has a property of projection operators, the product of sigma rho and rho sigma is 0. Okay. So this is just a preparation. to derive the RPA. So now let us derive RPA from TDHF. So now what we do is the following. So, okay, if you remember, after the variation of second quantized form of Hartree-Fock theory, you have this kind of equation, so this Hartree-Fock condition. And in case of time-dependent Hartree-Fock, in this case, you have this IH bar del T, the density matrix. Okay, so this is very similar. And now we introduce some external perturbation described by FT to the Hamiltonian. So this induce some perturbation to the system. And we assume that this, according to this perturbation, we have some small amplitude density oscillation around the equilibrium density, rho zero. So it means that this time-dependent density, one-body density here can be written as a ground state value rho zero plus some time-dependent fluctuations. Okay. So this is the setup. So we introduce the perturbation and density oscillates in this way around the equilibrium. So now we require that the system remains a Slater determinant for all times. Okay. So it means that the density matrix is idempotent. So we request that rho square at time t preserves this condition, rho t. Okay. So you can calculate this square of rho t, okay, by putting this, and then you can expand this, and then we can neglect this second order term, assuming that this is very small as compared to the others. And this rho zero, satisfies this idempotent property, so we can replace it by rho zero. So what we should require is here. So this rho zero delta rho and delta rho zero must be delta rho t to become this rho square to be rho. Okay, right? So this is the condition from this requirement. And we can, from this, we can see that, if you multiply rho zero and rho zero from the left and right of this delta rho, you can see that, okay, rho zero square is rho zero, and delta, so this rho, okay. The left hand side becomes rho zero delta rho zero, and right hand side becomes rho zero. Both are rho zero delta rho zero, right? And to make this equation to satisfy this equation, there must be this therefore this condition. So rho zero delta rho zero must be zero. And similarly, if you multiply sigma zero, you can get in this case, using the properties of projection operator, sigma zero rho zero becomes zero. And also this sigma zero rho zero becomes zero. So you can see that this must be zero. So it means that delta rho must have, whole and particle component of delta rho must be zero. So whole and particle means, okay, delta rho Well, yeah, we have this kind of structure, but whole part and part to part must be 0. And there are some numbers here. Okay. So this was derived from this requirement that density matrix must be idempotent for all times. Okay. And then we assume that this delta rho t oscillates at the same frequency as the perturbation. So it provides you this kind of form. So rho 1 is some density matrix, I mean some matrix, and it has some time dependence here. So rho 1 is a kind of amplitude, and this e to the power of minus I omega t and plus I omega t provides you some oscillation, time dependent part. So this is the form of delta rho. Okay. Now what we do is to use those equations for the TDHF equation. So from the assumption, rho t is rho 0 plus delta rho t. So if you take the time derivative, yeah, it provides you only this delta rho t, delta rho dot, okay, delta rho dot. Then right hand side is here. I just put rho t here, this rho 0 plus delta rho. And then you can expand this right hand side in this way. So first term is just okay. So we expand this h rho 0 plus delta rho up to the first order. So h rho 0 plus this delta h delta rho times delta rho. And then you can put this equation into this commutation relation. Okay. And you get this first term, it is just a rho 0 term. And you will get also this h rho 0 times delta rho t here. And so on. Okay. And we see, let's see term by term. Okay. And from the Hartree-Fock condition here, this first term vanishes. Okay. And here, F delta rho term can be neglected because it is the second order in delta rho. Or yeah, we assume that the perturbation is small. So perturbation times delta rho is second order. So we can neglect. Okay, so the remaining terms are those three terms. And let's see what happens here. So H delta rho term. And you can put the form of delta rho in this way. And remember that the Hamiltonian matrix H is diagonal in the Hartree-Fock state, in the ground state. So this HKL can be replaced with single particle energy, and it has only the diagonal components. So you can use this condition, and the first term is H delta rho, and the second term is minus delta rho H. So this is just a commutation relation. And you can calculate, you can take the summation over k, and then you can get this equation. So you have the difference between particle and whole single particle energies times this perturbation. And now we are calculating particle whole components. So those are equation, matrix equation, and now I just take the particle whole mi component of both sides. So here I put the mi, the subscript mi. And here you can do it in a similar way, but okay, so this, you can expand it in this way. So this is just a commutation relation. So first term and second term. And then you can use this condition of or peculiar form of this one-body density matrix, and it is only one for the whole component. Then, so it means that this k, index k, must be a whole state. And similarly, you can see that this part indicates that this rho zero or particle k component. But as I mentioned, this rho zero, one-body density matrix has component, only whole components. So this second term vanishes. So second term is zero because of this particle component. This is zero already. So the first term remains, and you can take the summation over k, and you get this form, and then you can put the form of delta rho here. So you have this equation. And finally, you can check what is this f rho zero term. And here, you can put again, so f rho zero minus rho zero f, but in the same reason, rho zero f term vanishes because of this particle side is zero. So you have only this equation here. And here, okay, so I just put the time derivative, I operate this time derivative for delta rho, and then you have, minus I omega from this exponential, and it becomes h bar omega rho 1 exponential minus I omega t. So you have you have calculated all the terms. And then, you can try to rearrange those terms. And I just put those terms that we derived, and you can see correspondence between this equation and the RPA. So if we write down this term as a A matrix here, and this term as a B matrix, and then we can derive the similar equation for the whole particle components. We can repeat in the same way, and you can get this equation. And regarding this delta H delta rho as V bar, and rho 1, this particle whole component and whole particle components at x, y amplitudes, then you can see this equation coincides with RPA. Okay. So in this way, based on TDHF equation and assuming small amplitude limit, small amplitude perturbation, and small fluctuation around the equilibrium density, we could derive the RPA equation from the TDHF. Okay, so this is second part of my lecture. And okay, so TDHF and TDDFT are not restricted for small amplitude limit. So this is just a derivation of RPA for the small amplitude limit. But we can apply TDHF and TDDFT to describe more complicated nonlinear dynamics. Okay, so in the rest of my lecture, I will show some application of TDDFT and TDHF for the low energy heavy ion reactions. Okay. Let me first explain what is interesting or what kind of phenomena emerges in low energy heavy ion reactions. Okay, so low energy heavy ion reactions can be regarded as non-equilibrium quantum many-body dynamics. Okay, so we collide two nuclei, projectile and target. Yeah, so this is very important actually because anyway we have to to study excitations and some properties of finite nuclei or to synthesize new elements or to produce some new isotopes, we have to collide two nuclei and induce heavy ion reactions. Okay, so the parameters that characterize the heavy ion reactions are charge and neutron number of colliding nuclei, Zp, Np, Zt, Nt, and of course the incident energy and the impact parameter. So impact parameter is the parameter that describes the non-centrality, let's say, of collision, or it is related to the angular momentum of the reaction. Okay. So in case of, okay, what happens? So in case of the reaction below the barrier, so incident energy is small as compared to the Coulomb barrier, or yeah, it is above the Coulomb barrier, but with finite impact parameters. In such a case, we have quasi-elastic scatterings. So in such a case, two nuclei do not collide deeply, but they can exchange some nucleons because nucleons are quantum mechanical particles. So the single particle wave functions can transfer, from one nucleus to the other. And in this case, the excitation energy is quite small. That's why we call it as quasi-elastic scattering. And yeah, so it can induce some few nucleon transfer. But okay, so in the case above the barrier, two nuclei collide and touch, and kind of capture takes place. So two nuclei are merging, and it forms some kind of dinuclear system. So a composite system of two nuclei. So you can regard this as the one elongated nucleus. Okay. So in this case, you have capture and dinuclear system formation. And in this case, you have a lot of energy dissipation. So nucleons are exchanged rapidly, and yeah, many nucleons are transferred. Okay, so it induces kind of multi-nucleon transfer reactions, and energies are dissipated from the relative motion to the internal excitations. And the angular momentum is also transferred into the internal degrees of freedom. Okay, so and after some time, it can deseparate to form two individual nuclei. Okay, so you can regard it as deep inelastic collision. So since we have a lot of energy dissipation, so kinetic energy is much lower than before. So this is deep inelastic, and also it can the kind of nuclei are different because of the multi-nucleon transfer reactions. And also, we can have the so-called quasi fission, which I will explain later. So a lot of nucleons can transfer after the dinuclear system formation. which is called quasi-fission. Okay. And after capture, of course, it can fuse, forming a single nucleus. So to have a fusion reaction, the so-called fusion reaction, the dinuclear system must overcome an inner barrier. So there is some barrier to make two nuclei get fused. But after overcoming an inner barrier, we have compound nucleus formation. Okay, so this is a fusion reaction. So what is compound nucleus? So it is a kind of summarized, complicated, superposition of excited states. And yeah, after compound nucleus formation, it loses the information about the entrance channel. So it is the assumption of compound nucleus, but so after the compound nucleus formation, we lose the information of entrance, what two nuclei are colliding. So in other words, we can change the projectile target nuclei, but making the same total number of protons and neutrons are the same. In such a case, you can get the same compound nucleus with different projectile target. And yeah, assuming that the information of the entrance channel is lost, then you have the same compound nucleus. And after fusion reaction, as you can see, this composite system can be highly excited. So it can decay by fission. So fission is the splitting of this nucleus into two. So this is the so-called fusion-fission reaction. So the point is, in the quasi-fission process, still we have information of the entrance channel, the colliding nuclei, but after compound nucleus formation, we lose this information. So it is called fusion-fission process, distinct from the quasi-fission. And of course, it can emit some nucleons, like neutrons, protons, and so on, some light particles. It is called evaporation process. And those evaporated nucleons can take the part of excitation energies. So this excited compound nucleus can cools down, and it eventually becomes some kind of cold ground state nucleus. So this is the so-called evaporation residue. Okay, so this is a true, fusion reaction. This is a fusion, but this is after evaporation, and it makes kind of stable or some composite system with low excitation energy. Okay. So in this way, so this is not the all processes emerging in the low energy heavy ion reactions, but in this way, depending on the incident energy and the impact parameter and the combination of projectile target nuclei, there appear a lot of reaction processes. Okay. And one can describe each of them using some phenomenological models or reaction theories. But using TDDFT or TDHF, we can describe many of them in a unified way from the microscopic nucleonic degrees of freedom. Okay. So this is the kind of overview of low energy heavy ion reactions. And now, okay, let me explain how to describe heavy ion reactions in TDDFT or time-dependent Hartree-Fock theory. Okay. Again, once energy density function is given, we do not have any adjustable parameter. So we just use the same EDF to describe reaction dynamics. As a first step, we prepare the ground state wave function by solving the constant equation or Hartree-Fock equation with effective interaction. So those two nuclei are projectile and target. And yeah, we solve it in real space. Okay. We discretize the three-dimensional Cartesian coordinates into some uniform grids. And we solve this constant equation. And we get the wave functions of projectile and target nuclei. And we put those two nuclei into a larger box, okay? And we apply some boost or we apply some momentum for those two nuclei. And then we evolve it in time. So by solving the TD time-dependent Cauchy equation. And then you can see what happens during the time evolution. That's it. So in this way, we can describe the low energy heavy ion reactions in real space and real time by solving this TDKS equation. Okay, so it is quite simple. Okay, now, okay, here I just show, I'd like to explain what kind of quantities can be described within TDHF or TDDFT. Okay, so assume that you collide two nuclei. So of course, those nuclei are quantum mechanical objects with internal degrees of freedom and very complex quantum mechanical processes will be taking place during the time evolution. But after the reaction, in the end of the day, you will get some reaction outcomes. So this is not only the theoretical assumptions, but also if you do the experiment by accelerating some nuclei and bombarding it to the target, and then as a result, you will get some a bunch of reaction outcomes, and you see some distributions. Okay, and what TDHF describes very well is actually this. So it provides us the main average most probable reaction outcomes. And actually, it cannot well describe the distribution of the observable. We can get some part of distributions, but it is underestimated. Yeah, but nowadays we can improve this expression by introducing kind of time-dependent RPA or introducing some many-body correlations and fluctuations. We can get very nice description of the distribution as well. But this is beyond the scope of this lecture. So in the following, I will show how TDHF works in practice. Okay, but it works quite well. Okay, first one is multi-nucleon transfer reactions. Okay. So now I just show some animations. Okay. So this is a case of collision of nickel 58 on lead 208 at energy very close to the Coulomb barrier. Okay, so those are two cases with different impact parameter. So this is more close to the head-on collision, and this is impact parameter 4. It is more shifted, as you can see. Okay, so let me first show this case with larger impact parameter. So in this case, two nuclei do not collide. Okay, two nuclei are approaching and they separate. But okay, so let me Okay. So in this, even for this case, actually, the single particle wave functions are transferring from one nucleus to the other through the tunneling processes. Okay. So even for this case, this is like a quasi-elastic scattering that I introduced. Yeah, we have transfer of a few nucleons, yeah, between two nuclei. So now let's show this case with smaller impact parameter. So in this case, we have collision of two nuclei. So two nuclei form a neck and strongly, largely deformed. And nucleons are exchanged actively. And two nuclei are connected to each other for a quite long period. It is about a few zeptoseconds. So zeptosecond is 10 to minus 21 seconds. Anyway, so after certain time, we have the separation. So as you can see, the number of nucleons are different. So because of the transfer from one nucleus to the other. So this is, yeah, one can regard this as the onset of Keisai fission. But anyway, so in this way, we can describe quite different transfer dynamics based on TDHF. So here, I just show how many nucleons are transferred during the time evolution. Okay, so this figure shows the average number of transferred nucleons as a function of impact parameter. Okay, so delta n indicates, okay, so the positive value indicates the transfer from lead 208 to nickel 58. And this minus sign indicates the opposite, the transfer from nickel to lead. And red symbols indicate the neutrons, number of transferred neutrons, and green symbols correspond to the number of transferred protons. Okay. Okay, so let's see first this region where impact parameter is relatively large. So in this case, as you can see, the red and green symbols show, opposite signs. So neutrons and protons are transferred in an opposite direction. And it can be understood as a charge equilibration process. So neutrons and protons are transferred in the opposite direction. And naively, it can be understood as, yeah, the difference between the Fermi energies or chemical potentials of two quantum nuclei. And in this case, neutrons are transferred from lead to nickel, and protons are transferred from the nickel to lead. So in this way, during the collision, when two nuclei approaches, the nucleons around the Fermi level try to gain energy by transferring from one nucleus to the other, and this is the result of the so-called charge equilibration process. So neutrons and protons are transferred in the opposite direction. Okay, and let's see what happens at smaller impact parameters. So as you can see, the behavior is somewhat different. So at around 3 impact parameter, 3 femtometer, two nuclei start merging and forming a neck. And after neck formation, the two nuclei evolve. The shape is changing, and when two nuclei dissociate or split into two, when neutrons and protons around the neck region are transferred or absorbed to the lower fragment. So in this way, the neck formation and breaking dynamics provides you the transfer of neutrons and protons in the same direction. So that explains this behavior. So after charge equilibration forming a neck, the system splits into two by transferring neutrons and protons in the neck region to the lighter fragment. So depending on the impact parameter, as you saw, TDHF provides you the distinct two different transfer mechanisms. Yeah, in this way, charge equilibration and neck formation breaking. Yeah, without any, microscopic way. So this is actually complex reaction dynamics, but you can get this kind of insight from the TDHF calculation. And actually, we can compare with experimental data. And I will skip the detail, but we can calculate the cross sections actually. So let me just introduce the idea. So we can describe using TDHF the microscopic reaction dynamics as I showed previously. Okay, it occurs in 10 to 21, zeptosecond to 10 zeptosecond in this time scale, 10 to minus 21 to 10 to 20 seconds. But after the reaction, two nuclei can be highly excited. And as I mentioned, the excited fragments can decay through fission or evaporation processes. So actually, this kind of decay processes occurs with much longer time scales, like 10 to minus 18 or 10 to minus 60. So it is quite different. So it is not reasonable to describe these kind of processes within TDHF. So here I just propose to use some statistical model that can describe particle emission and fission, this decay modes, the so-called Gemini, and to describe this part. So to this end, okay, this is just give you an idea. So after the reaction, you have a single Slater determinant like this. And we can perform kind of the so-called particle number projection. So this here, PNPZ represents the particle number projection operator, but it is like, given here. So the N is a number of particles to be projected, and this N hat represents the number operator acting only on one of the fragments in this region. So it indicates that we can extract or project out certain components of wave function which has specific particle number in this fragment. So we can perform this kind of calculation, and we can calculate the transfer probabilities, and by integrating over the impact parameter, we can calculate the cross section, which can be directly compared with experimental data. And those are just the information that we can calculate, or also some quantity like excitation energy and angular momentum of the reaction product with specific transfer channel. And we can use this information to describe the secondary de-excitation processes. And let me show how it works. So by applying the particle number projection technique, okay, what we can get is the transfer probabilities. Okay, so this figure shows the transfer probabilities of neutrons and protons as a function of impact parameter. Okay. And there are many lines that correspond to different number of transfer nucleons. So for instance, when impact parameter is large, two nuclei do not collide. And in such a case, you see this red line becomes almost 1. So at large impact parameter, the transfer doesn't occur. So zero nucleon transfer becomes, probability of zero nucleon transfer becomes 1. But as the impact parameter decreases, then two nuclei start to exchange nucleons like this. So you can see some 1 neutron transfer probabilities and 1 proton transfer probabilities as well. But because of the Coulomb repulsion, proton transfer has shorter tail as compared to neutrons. And when two nuclei collide, nucleons start exchange actively, and you can see two nucleon transfer probabilities and 3, 4, 5, 6, blah 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 at short impact, small impact parameters. And then you can integrate. Okay.
On the proton graph, what is that initial dip between 1 and 2?
1 and 2.
Yeah.
This dip.
No, the first dip.
First, 1 and this. This. This one.
Yes.
It means that, So, as I mentioned, the proton transfer, here. So, after charge equilibration, okay, so when two nuclei collide, neutrons and protons are transferred in the opposite direction. But after this charge equilibration,
Okay.
it develops a neck and it transfers in the same direction. And as you can see, it becomes a minus and then change the sign. So it crosses at 0. So there is a region where this, zero proton transfer first decreases, but it increases. And then after that, the plus, it is not sure, but positive nucleon transfer probability develops. And it makes it steep.
Okay, thank you.
So anyway, from TDHS calculation with particle number projection, you can get this kind of complex probabilities as a function of impact parameter. And then you can perform you can integrate these probabilities over the impact parameter to calculate the cross section. And we can compare with experimental data. So this figure shows the cross section to produce various isotopes that are produced after this reaction. So experimentally, experimental data are those red points. So experimentally, after collision, for instance, you can find the nickel isotopes. Okay, this is as a function of Newton number. So proton number is 28. 28, but the Newton number can be different. And at the same time, you can find different elements like cobalt, iron, mangan, chrome, vanadium, titanium, right? And then as a function of Newton number, you have cross section. And those red and blue line corresponds to the result of TDHF calculation with particle number projection. And as you can see, in some cases, so those cases, you can see some deviations. But for those processes with small number of proton transfer, it agrees. It is not so bad. Okay. So again, in this case, we do not have any adjustment of parameters. We just use the same energy density function and perform the calculations, and we get this kind of cross sections. And to improve the description for this many proton transfer, we need to go beyond TDHF to include the many body correlations. But nowadays it is possible. But anyway, with this time-dependent Hartree-Fock or TDDFT, we can calculate complex processes of multinuclear transfer in this quantitative way. Okay. So next, let me show the example of quasi-fission processes. So let me remind you what is quasi-fission. So it is actually related to the synthesis of super heavy nuclei. So first of all, quasi-fission is a fast, as compared to normal fusion fission. It is fast fission process before the compound nucleus formation. Okay. So after capture, of course, it can, if two nuclei overcome an inner barrier, it can undergo fusion. And fusion means we have compound nucleus formation. So we lose the information of the entrance channel. But in case of collision of heavy nuclei, because of the strong Coulomb repulsion, actually, it is very difficult to overcome, to make two nuclei get fused, okay? So fusion probability is very, very small. And this fission process, before compound nucleus formation becomes dominant. Okay. And to synthesize super heavy nuclei, what is relevant is this evaporation residue cross-section. So as I mentioned, this evaporation residue cross-section is, okay, to make an evaporation residue, we have to make two nuclei, capture. Capture process must happen. And after the capture, compound nucleus must be formed. And this is the probability of compound nucleus formation. And after compound nucleus formation, it must survive against fission. So this is the survival probability. So this is the product of these three factors, and this you can get more or less the evaporation residue cross-section. And in case of heavy nuclei, this probability of compound nucleus formation is really small, and this makes this quasi-fission process is a dominant process. And actually, as I mentioned, the time-dependent Hartree-Fock theory can describe the main, most probable reaction outcomes very nicely. And this case, quasi-fission is the such main reaction outcomes. Okay. So based on TDHF, we can study quasi-fission dynamics, and it is, it is a counterpart of the compound nucleus formation. So it is relevant to the super heavy element synthesis. Now, again, let me show typical examples. Okay, this is again animations. So this is a case of collision of nickel-64 on uranium-238. So this is uranium-238, which is, actually this is the oblate. So this is like a rugby ball shape. So actinoids are deformed in this way. And in this case, since uranium-238 is deformed, we can change the orientation of this uranium-238. So, okay, so this is a tip collision where this nickel nucleus collide with this tip of elongated side of the uranium-238. And this is a side collision where nickel collide with this equatorial side, this shorter side of the uranium-238. Okay, so incident energy is the same, and impact parameter is the same. The difference is orientation. So I just move both animation at the same time. So in both cases, two nuclei collide deeply, but in case of, tip collision, as you can see, the dinuclear system elongates more as compared to the side collision, and it splits into two in a shorter period. Okay, But inside the collision, we have more compact dinuclear system with thicker neck, and two nuclei are merged, connected to each other more longer period, and it split into the two. So those are typical K-side fission processes. And in those cases, you can calculate how many number of nucleons are transferred. So in this case, about 36 nucleons are transferred on average. And in this case, about 50 nucleons are transferred on average from lead to weight, from uranium to nickel.
Where is it shown effects to we
Yes. So yeah, actually, after time evolution, yeah, we can see that this heavier product in tip collision has Newton number 126 and proton number 82, close to the lead to weight.
Okay.
So dynamically, such quantum shell effects emerge, and it affects the reaction outcome. So in this way, as you can see, the phase fission process is very complicated dynamics. Okay, so now the question is if this kind of process really happen experimentally in reality. And we can compare this kind of reaction outcomes with experimental data. So this is, okay, here I show the total kinetic energy, TKE, of reaction outcomes. So it is a kinetic energy of outgoing fragments as a function of mass number of the fragments. And left hand side I show TDHF result, and right hand side I show experimental data. Okay, let me explain one by one. So as you can see, you have this kind of peaks of TKE at around mass number 64 and 238. So those correspond to K-side elastic scattering or larger impact parameter. So in such a case, the energy dissipation doesn't take place. So excitation energy is small. So kinetic energy is large. So we do not have energy dissipation. So we have these peaks, and those peaks corresponds to this incident energy, right? Okay. In the center mass frame. So this is laboratory energy, but this is the center mass energy. Okay. Then when impact parameter decreases, two nuclei start colliding and energy dissipates into the internal excitation. So those peaks goes down rapidly, and after energy dissipation, we have neck formation, and we have massive nuclear transfer from lead to weight. From uranium to nickel. So massive nuclear transfer from heavier nucleus to lighter one induce this kind of trend. It goes to more mass symmetric products. Okay. And by the way, those different colors corresponds to different orientations. So I changed tip and side and the other side orientation. So those corresponds to anyhow three typical orientations. So now you can compare this result with experimental data. And in experiments, of course, there are abundant distributions, but you can compare the mean values, okay? So the amount of energy dissipation and this trend towards mass symmetry, you can see some agreement. So it happens in reality, in femtometer scale. So in this way, TDHF provides quantitative description of K-side fission dynamics without any other sort of parameters. So it is very powerful tool. Okay. Now, as I think this is a final example. Now I will, in the rest of 10 minutes or so, I will discuss application for the super heavy element synthesis. Okay. So how to synthesize new elements? So we make a nucleosynthesis kind of experimentally. So we collide two nuclei and make a fusion reaction. So to this end, we use accelerator facility like RIBF. So this is the RIBF factory in Riken, and Riken is in Saitama Prefecture, close to Tokyo. And okay, so this accelerator facility is located in the underground, and it is quite large. And to have a taste, so you can see this is a picture of superconducting ring cyclotron SRC, and this is the world biggest superconducting ring cyclotron. I mean, this has Guinness record. Okay, and okay, so you can see this. Many people are on this SRC, and actually, since the operation starting in 2007 or so, this facility has been a world-leading factory of unstable nuclei. So nowadays, some countries are developing, constructing similar facilities, but I think still it is a world-leading factory of unstable nuclei. So actually, Japan has been a leader of, leading facility of unstable nuclear physics. Okay. So this is the introduction to the super heavy elements. So actually, the periodic table is growing from time to time, as you may see. So this is old periodic table. Now, actually, when I learned periodic table when I was much younger, those elements more than, exceeding elements 100 or so, did not have name. So there are some name without specific name of the elements. Okay, so now in November 2016, we have added those four elements: nihonium, moscovium, tennessine, and organeson. And this element 113 is named nihonium, which was synthesized at Riken, and we got the name license, and we put this name nihonium. So Nihon is this name of Japan in Japanese. Okay, so this was very scientifically, not only scientifically, but also as historically it has very important meaning. So those represent the flags that find the new elements. And this is only Asian country that have been finding, had a name license. And this is nihonium. Okay. And this guy is Morita-san, which was the leader of these experiments. Okay. This is just to mention that, okay, so the year 2019 was the 150th anniversary of the periodic table. And we had a ceremony in Japan, and there are, they are the guys that found the elements, super heavy elements. So those are nuclear experimentalists, including Morita-san. Here is Morita-san. So I was there, and I took this picture, and I bought this necktie. So as you can see, those has special design with Mendeleev beam 150th International Year of Periodic Table 2019 and 4 elements. So when I have a chance to wear a necktie, I always use this. But nuclear physicists rarely wear suits, so it is very rare case. Anyhow, so let me now explain how nihonium was synthesized experimentally. So the experiment was started in September 2003. And yeah, it is 10 to 12 nuclei per second. I mean, beam of nuclei are irradiated on the target. So beam was zinc with atomic number 30, and the target was bismuth with atomic number 83. So if you add those two, it becomes nihonium. But it is not easy. So after 100 days of irradiation of this number of nuclei, then they got first signal. So in about a year, they have one event that maybe one element 113. But after 0.3 milliseconds, it decays by alpha emissions, and it in the end end up with fission. So by detecting all the alpha particles and this fission product, experimentalists try to show that that nucleus formed after the reaction is really nihonium. But okay, so after they continue the experiment, and after 100 days of irradiation, they got second event, which is very, it is a similar decay. However, this dubunil undergoes to fission, and this fission modes are some rare, minor events, and this was not enough to show the formation of nihonium. So then they continue the experiment with upgrading the detectors and setups and so on, but it takes about more than 7 years, right? But after this experiment, they finally get third event. And in this case, dubunil undergoes to alpha decays, and those agree with existing data. And finally, with those 3 events, we got the naming license, and nihonium was approved. Okay, so now, okay, so here I just show the northeast part of the nuclear chart. So here is lead-208, and here is uranium somewhere. Uranium is somewhere here. And those are super heavy elements, super heavy nuclei. And those colors indicate the half-lives. So actually, we expect that the next doubly shell closure exists in the super heavy region, which will stabilize the super heavy nuclei, the so-called island of stability located here. But we have so far could not produce nuclei at the island of stability. But we are trying to reach this region. And this cartoon depicts the situation. Here is island of stability, and this is sea of instability, and we are several reaction mechanisms. But to go beyond organeson and to reach island of stability, of course, we do need theoretical predictions. Okay. So since time is up, I will just go quickly and summarize. Okay, so this is one of the simulation that may synthesize element 119. So in this way, we can calculate the reaction of some specific nuclei, and we can extract various quantities that may be useful to synthesize experimentally. Okay. So this is final topic, but I may go very quickly. So yeah, as I mentioned, TDHF can describe this main process, but in other words, it cannot describe well this compound nucleus formation. So yeah, one can try to combine some phenomenological model with TDHF. So this was done several years ago. So using TDHF, we can get this contact configuration, and we can connect this information to the model that can describe the upfield diffusion over the inner barrier to produce the compound nucleus compound nucleus. So I will skip. I just give you this image, and I skip the details of the model. And okay, let me summarize my talk, this lecture. Okay, so the point is, okay, the TDHF equation or Kohn-Sham equation can be derived by minimizing this kind of action. But the point is, we just use this energy density function here. And okay, we do not adjust parameters to specific reactions. So we just use energy density function that can describe all the properties of finite nuclei and nuclear matter. So it is very powerful. And as you saw in this lecture, it works pretty well to describe various reactions at low energies. And the message is following. So TDHF can describe main reaction outcomes like nuclear number of transfer nucleons, TKE, scattering angles, contact times, and so on. But it can fail to describe the distribution. But it is nowadays possible to improve. I didn't explain, but we can introduce some fluctuations and variations on top of the TDHF, and we can improve the description. And we can extend this approach to combine some other models to describe the compound nucleus formation and so on. But anyway, it is very powerful too to study the complex reaction dynamics of low energy heavier reactions. And okay, this is one of the important methods. So we can study non-equilibrium quantum dynamics based on TDHF or TDDFT, based on microscopic degrees of freedom. Okay, so this ends my lecture. And if you have questions, please ask. And if not, you can leave.